I know in the previous video there was a lot to take in, but hopefully in this example things will get much clearer. So let's imagine we have gene expressions for mice, right? So here it's going to be gene 1, let's say gene 1, and here we have gene 2. We are just going to deal with 2 genes for now, right? We have mouse 1, mouse 2, mouse 3, mouse 4, mouse 5, and then mouse 6, like this, right? Cool. Let's say in mouse 1, gene number 1 is expressed, it is like, let's just say 10 times. We can say 10 times 11, 8, this one 3, 2, 1, this one 6, this gene number 2, 5, 2, 3, 2.8, and 1. Of course, we can plot this on a Cartesian plane, right? We can definitely put this on some Cartesian plane. The x-axis can be gene 1 expressions, and then the y-axis gene 2 expressions, right? So we're going to say 10 and 6, 11 and 4, and stuff like that. What we're going to see when we plot these is mouse number 3 is there, mouse number 1 is there, mouse number 2 is there, and then here we're going to have mouse number 4, mouse number 5, mouse number 6, mouse number 6. Cool, right? Here we can already tell there are 2 clusters. There are relatively 2 clusters, as we can tell. These 3, the first 3, they have high numbers, and these for both gene expressions, and the last 3 have low numbers for both gene expressions. Cool. PCA can tell us which mice are similar, and also which variables are important in this when we do this clustering. It can tell us which mice are similar and which ones are similar to each other, and which variables did we use to determine that, which variables are important. So let's do an example for CP using this for PCA. So let's do this in steps. Step 1, like we said in the previous one, normalize. Step 1, we have to normalize, right? I like to use I'm going to use the graphs. I'm going to draw a lot of graphs in this video because I want it to be visual. If you can visualize it, hopefully it will be better. It will be easier to understand. So let's visualize it. Let's visualize it. When we get here, what we're going to do is, when we normalize, let's get the mean gene 1, and then we get the mean gene 2. Let's drop numbers for now. Let's drop numbers for now, right? Mean gene 1 and mean gene 2. We have stuff on a plane where this is obviously gene 1, this is gene 1, and this is gene 2, right? Gene 2. And here we had 3, 1, 2, and we had 4, 5, 6. So when we calculate the means, what is the mean for gene 1? Let's just say the mean for gene 1 is going to be somewhere here. This is the mean for gene 1, and here is the mean for gene 2, right? When we put it together, when we put the x value, or the gene 1 value and the gene 2 value, we are going to get this point here on the Cartesian plane, right? We're going to get that point. So this point is our center of the data. So that's going to be the center of the data, right? Center of the data. Cool. Happiness. I think we are happy with that. What we are going to do now is, and I'll explain mathematically what that means. We are going to shift every point. We are going to hold each and every point on this graph and shift it such that this center moves to the origin. We are going to move it to the origin. we are going to hold everything that we can see, hold it in place, but just shift or translate the center so that it goes to the origin. So we're going to end up with a situation something like this. We're going to end up with our center at the origin, right? We're going to end up with the center of the origin, but everything has moved as the center was also moving. So we're going to have our 3 here, our 1 here, and our 2 here, and we are going to have our 4, our 5, and our 6 here. That's what we're going to have, right? This is what we're going to have. We didn't change anything. The distances between the points is just the same. This was normal translation. If you did a bit of maths, let's say in high school, translation does not change anything. It's just a movement, or horizontal, vertical, sliding, whatever it is, just a movement. But the distances are still the same, the scales are still the same, right? That's what we did here. And mathematically, this is where in the previous video we were doing population minus the pop mean, and then the ad spend minus the ad mean. That's basically what we're doing. Because if the population, it becomes the mean minus the mean minus the mean, it becomes 0. So for each of these points, we're going to subtract the mean. Mouse number 5 minus the mean, it goes somewhere there. 4 minus the mean, it goes somewhere there. 6 minus the mean, it goes somewhere there. 3 minus the mean, it goes where it is now. 1 minus mean, it goes there. And then 2 minus the mean, it goes there. And the mean minus the mean, it goes to 0. So basically we just translated. So that's what we mean translated. It's exactly what we did previously with the subtraction, like pop minus the population, add minus the add, So here you can even add your, if you wanted to see it in a table, you can add GENE1 translated, get the mean, and then for each of these points subtract the mean, and write them here, Those are the values that we're dealing with now. Those are the values that we are dealing with now in this. And that is what we're going to continue dealing with, where the mean is at the center. So we have mean centered this. This is mean normalization. Mean normalization. Cool. After we've done mean normalization, let's go on to step number 2. Right? Step 2. Now with centered data, we're going to try fit a line to this data. We're going to try fit a line to this data. So let me do that. I'm not going to draw in the mean because we know that the mean is at the origin. So that one we are happy with. Just going to put points like this because we already know 4, 5, 6, right? I'm going to try fit a line to this data. No, okay. I do not know what line to fit, right? So I'm going to draw a random line. Just going to draw a random line. Let the line be like this, randomly. That passes through the origin. Please think of this line as passing through the origin. It's so difficult to draw on a graphics tablet. So this line is passing through the origin, right? And that's the line that I fit. I've just guessed the line. Just guess the line, right? What we are going to try and do is we're going to ask ourselves, does this line fit the data correctly? By eyeballing it, maybe not. So we are going to rotate this line. We're going to rotate this line into a new line that passes through the origin. We are rotating it by the origin, at the origin, right? Around like that, and then we ask ourselves, this new line, does it fit the origin? Does it fit the data? Probably not. We rotate it again. So until we end up with a line, maybe like this black line here, this solid black line. And then we are going to ask ourselves, does that line fit the data? Looking at it, I'm emphasizing looking, yes, it looks like it fits the data. This line fits the data, right? Fits the data. And now we are back to those question marks that we had in the previous example. What exactly does it mean to fit the data? Well, PCA, it measures this in two ways. it measures this in two ways. Way number one is you can either measure the distance from the points to the line, and find a line that minimizes these distances. Maybe some of you are guessing this already. Minimizes this, right? So we'll be like, for each point, so what we can do, we'll be like, okay, for each point, for our original line, let's get the distances to that line. We draw our perpendicular lines, our projections, like, okay, that is the distance for that point. Okay, that is the distance for that point. That is the distance for that point. For that, and so on, for that point. And then we're trying to find a line that minimizes this. These are large distances. Okay, let's do it for the second line. For the second line, those distances, yes, they are looking shorter now, shorter than the original one. I think we can see that already. Okay, cool. We are getting somewhere. For this black one, the distances, see, the distances to that line, oh my goodness, they are the smallest. Can you see? They are very, very tiny compared to the other ones that we had. So we'll be like, yes, that is our best fit line. That is our best fit line that minimizes the distances. Minimizes the distances from the points to the line. And you know that when you're saying from point to a line, you have to do like at 90 degrees. You draw a 90 degree line from the line you're going to the point. So we can we can measure the fit of the data using this. Or a second method is by maximizing distances of projected points from the origin. This is not very intuitive. Maximizing the distance of projected points from the origin. Why the origin, right? That could be a question. Let me use blue for this. For this, when we're using this original line, this first line, right, that we drew, this was the point where we projected this point. When we projected on that line, it came to this part here. And this point was projected here to this part here at 90 degrees, right? And this was projected here, and then that was projected there. So when we're saying maximizing the distance of the projected points from the origin, what we're basically saying, these distances, that's the distance for that first point, and then this distance for this projection, this distance, and the distance to the other point, to all the points, these distances from the origin, they should be maximized. If we can maximize those, we have found the line that best fits the data. When you look at these, they seem like very different. They yield different results. Like, how are they the same? They actually are the same. Let's see why they are the same. Let me convince you that they're the same. The reason why I have to convince you they are the same is because PCA prefers to do it this way, maximizing the distance of projected points from the origin. It is much easier to do it this way than to do it this one. This one, intuitively, yes, the first intuitively it makes sense, but then PCA, it's easier to actually do it using the second method. But first, let's convince each other that those two are the same. Let's do that by, let's imagine we have a Cartesian plane with a point that is here, the point that is there. This point is fixed on the Cartesian plane. We know that it is fixed on the Cartesian plane. It is not moving, not going anywhere, so it is fixed. So which means the length of this line is the same. It's going to be the same no matter if we move the Cartesian plane here. The length of that line is going to be the same, right? We know that, right? So imagine we had two lines. Imagine we had two lines. I'm going to use blue. Imagine we had a line like this, because that's exactly what we have in our situation. We have multiple lines, and we want to see which one is the best line, or we want to be convinced that doing the first thing is the same as doing the second thing. So we have that line. Let's draw there. So for the projections, I'll be using green. Let's project this point to that line. Imagine this is 90 degrees. Yo, it's not going to be 90 degrees. No, that's way too much. That's way too not 90 degrees. Okay, let me try see if I can just erase this that I did here. We want it to be 90 degrees. I'll try and make it 90 degrees. So cool, let's try make it 90 degrees. So maybe the projection will be something. No, let me just use blue. We said the projections we're going to use green, right? So the projection is going to be something like this. That's much better. Much better. Cool. It's going to be something like this, right? To that line. Perfect, right? Now what we're going to do is let's label the sides here. Let's label the sides. I'm going to use orange to just label the sides. Let's label the sides of this right, because now we've created a right angle triangle. Can you see? Going to the origin to this projector point to the point itself. So let's call this A, and we're going to call this green side B, and then this blue side C. Right? Using Pythagoras theorem, using Pythagoras theorem, a squared is equal to b squared plus c squared. We are all happy. We are happy. But what does that mean? Right? A is a constant. It is not changing. A is a constant. It is solid, not changing. What that basically means is if B increases, to maintain A being a constant, it means C squared needs to decrease, right? If B squared increases, C squared needs to decrease, because we said A is a constant, so A squared is a constant, right? If B squared decreases, then C squared has to increase. It just has to, by the same amount, to cancel each other out. By the same amount. It has to change, but in the same amount, but in the opposite direction. This is very important because intuitively we understand point number one, method number one. Intuitively we understand method number one, that we have to measure the distance that minimizes this. We have to find a line that minimizes this, right? What that basically means is we have to rotate B until it minimizes this green line. So maybe you are rotating B to be like this now. We are rotating B to be like that now. Because what are we trying to do? We are trying to minimize the distance between the point and the line. And that distance, we said that distance is the projected distance, which is this, the green line. So now this is the new B. I'm going to put B prime. Our A is constant. So can you see our C now? Our B has gone down. So what does that mean for our C? It means our C has to increase. And if you can look at it, the distance from the origin, the C is actually stretched out to here. It is stretched out to there. Our C was originally like this. Now it is increased. So the more we decrease B, the more we increase C. The more we decrease B, the more we increase C, because our A is constant. So the more we are trying to minimize the distance from the point to the line, the more we are maximizing the distance of the projected points to the origin. So here we are doing B, and here we are maximizing C. So I hope you are convinced that those two statements are actually mean the same thing. So the best line that fits the data, it either minimizes the distance from the line to the point, or like what PCA favors, it maximizes the distance of the projected points from the origin. Cool, so that's what we will be doing, maximizing the distance of the projected points from the origin. Right? So cool. Now that we are convinced that those two are actually the same, what we are going to do now is to calculate something. Now we'll move on to step 3. So we now know how to fit the baseline. The baseline is just to maximize the distance of the projected points. We now know how to fit the baseline. Alright? Or let me write it as a note here because it's very important. It is very, very important. PCA finds the baseline by maximizing the sum of the squared distances. Let me just explain this because I really didn't explain it. Distances from the projected points to the origin. Yeah, right. So basically, pretty much we are going to. This was just for one point. This was just for one point, right? Imagine we had multiple points. If we had multiple points, all of them are going to have their own C's. Their C's, the distance from the center. We're going to have a C here and a C here and a C. Not like yeah, but on the same line. Let me actually draw something. Let me draw something to just make this to make it clearer. So for our points, we had our 3 points were on this side, and the other points were on that side. Cool, and we had a line. That was going here. We had a line going like that, right? We had a line going like that, and then we did our projections. Our projections. So these were the projected points. These are the projected points for our data. These were the projected points. The projection for this point, and this becomes the projection for that point, and this becomes the projection for that point. Cool. So these are the projected points on that line, right? What we are trying to do is to maximize the distance of these points from the origin. Basically, what we're doing is we're saying, okay, for this first point here, your distance is going to be this one here, D1. That is your distance from the origin, D1. And what we're going to do is to say, and for the second point, we're going to say this is your distance, D2. And for the third point, this is your distance from the origin, D3. Same as this point, this fourth point, it has its own D4, this one has D5, and this one has D6. So what we are trying to do is we are trying to maximize the distance of these points from the origin. So what we are maximizing is we are going to maximize the sum of the distances of the projected points from the origin. So we are maximizing the sum. What is the sum? The sum, when you say we are maximizing the sum, this is what we're basically maximizing, is we are maximizing D1 squared plus, it's actually supposed to be sum of squared distances. Squared is very important. D1 squared plus D2 squared plus D3 squared plus D4 squared plus D5 squared plus D6 squared. The squared is going to be important because we do not want the negatives to neutralize the positives. We just square to neutralize the negatives. We haven't really changed mathematically. We haven't changed anything. We haven't changed anything at all. Maximizing will just be the same. It will be much easier it will actually bring out information from the data. Because imagine if we have a 5 and a -5, these are going to neutralize, and then we are going to struggle. We're going to struggle to deal with the 0. But then if we are going to maximize, we're going to compare like a 25 line with a 25 and a line with a 30. It's going to be much easier for us to compare. So we are going to find a line that maximizes this. We're going to find a line that maximizes that. Cool. These are the D1s, D2, G3s according to that blue line, right? According to that blue line. We can have, I don't know if you see yellow, but we can have another line like this. We can have another line like this. All these points are going to have their own Ds. We're going to have another set of Ds. We're going to calculate D1 squared plus D2. I'm writing in yellow. I really apologize. I don't know if you can see it, but what I'm basically saying is, according to the yellow line, those points are going to have their distances, and we are going to calculate what is the sum of those distances. Maybe with the black line, maybe the sum of the distances was what do you call this? Maybe it was 20. It was 25. Maybe some of the distances would expect it from what we can see now. The sum of the distances from the yellow line, we expect it to be higher than that. Just by eyeballing, we expect it to be higher than that. So the sum of the distances from the yellow line could be 38. And then we'll favor the yellow line over the blue line. We'll favor the yellow line over the blue line. We'll be like, nah, blue line, we have found a line that has maximized the sum of the distances, of the squared distances. I keep saying sum of the distances, forgive me. What I mean is sum of the squared distances. We'll be like, yeah, we have found a better line. And maybe we will do another line. We'll rotate, get another line like this, the black line. We find the sum of the squared distances again. Maybe here we'll find it's 50. Then we'll discard all the lines that we had previously. We'll be like, nah, this black line is the best one now. So that's how it finds best fit. And when we have found that line, this black line here, when we found that line that maximizes these distances, that is the line that is called the first principal component, or principal component number 1. That maximizes those distances, that is the principal component 1, or PC1, or the first principal component. Cool. Let me quickly delete this, delete whatever, because I didn't think I would get to the end of the page, but let me delete everything. Cool. So now that we have found our first principal component, right? When we have our first principal component, we can now just look at the gradient like we normally do. What is the gradient of the line, the slope of the line, right? We can look at the slope of that first principal component. Slope of PC1. In our case, let's just say it was 0.25. 1/4. And we know that on the x-axis we had our gene 1, and then here with our gene 2 in the y-axis, gene 2. So yeah, so it's going to be 0.25, like that. So what this basically means, right? Let's see. Let me see whether I wrote my notes correctly here. Let's see if I wrote my okay, yeah. So it's going to be, yeah, because our gradient. So let's look at how we calculate our gradient. I was getting confused because of the way I wrote these genes. I just wanted to say this is the x-axis and this is the y-axis. Yeah, that part was confusing me. Gradient is y over x. So this means that this is 1/4. This is 1/4. Cool. Because our x is our gene 1 and our y is our gene 2. Perfect. So if that is the case, right? If that is the case, then what that means is then for every 4 unit increase in x or gene 1, there is a 1 unit increase in increase in gene 2, right? That's how gradient works. 4 unit increase in y results in 1 unit increase in our y, right? What that basically means is the data is more spread out along the gene y, more spread. It means the data is more spread out along the gene 1 axis, because that is where the highest increase is compared to just a 1 unit increase in gene 2, right? It means now gene 1 has higher variability or larger variability. I think it's a larger variability. I think that's the correct English. I think it's larger variability. There's a larger variability than gene 2 axis, right? So our data is more variable along the gene 1 expression. What that also means is gene 1 compared to gene 2 is more important in describing data, in describing how data is spread out. So these are the conclusions that we're getting from just this, the gradient of the PC1 line. According to the PC1 line, data is more spread, and it's very important. According to PC1, data is more spread along the gene 1 axis line compared to the gene 2 line. The data has larger variability according to PC1 along the gene 1 axis. The data is more, gene 1 axis is more important in describing how data is variable or spread out. How data is spread out. That's just coming from that gradient of the PC1, right? But so to write the equation of the PC1, we will now just say how many units increase for G1 and the unit increase in G2. We are saying 4 unit increase in G1 in gene 1 plus a 1 gene 2. This becomes the equation of our PCI. Becomes of our PC1 over PC1, our principal component 1, or our first principal component. In the previous video, we are calling these the phi's. So that's how you get the phi's. The phi's are gotten from the gradient. They are gotten from the gradient itself. We're getting from the gradient of that principal component direction. Right? It's just the gradient of the principal component direction. Right? Cool. These are well and fine, but then if we are doing principal component with something called a singular, with something called an SVD, right? If we're doing linear combination with SVD, we have to scale down these, and I think it's just best practice. Whenever you do PCA, scale them down, or make them add up to 1. How do you make them add up to 1? You just divide by the summation of the squares. So my PC1 is just going to be 4 divided by the summation of this square root of the summation of the squares, or the norm distance, which is just going to be equal to this G1 plus 1 over square root of 4 squared plus 1 squared with gene 2. That's basically what you do. And you find that your PC1 is equal to 0.97 gene 1 plus 0.242 gene 2. That's pretty much it. This will be your first component, principal component line. This is your first principal component line, right? Cool, first principal component line. And as we said in the previous videos, these coefficients are called the loading scores. They are called the loading scores. After this scaling, what we have actually done is we had our points, right? And we said this line is the best fit line according to maximizing the distances, right? maximizing those distances. Cool, that is our PC1 or our first principal component. Cool. And what we have done by scaling here is we have created a special type of vector, a unit vector along this direction. We've created this unit vector along this direction. Unit vector just means magnitude 1. So we've created a unit vector along that direction, and this unit vector has a special name. It is called the eigenvector of PC1, eigenvector of PC1, or the singular vector of PC1, singular vector of PC1, singular vector of PC1. And we have another term that we can describe now, something called the eigenvalue of PC1. We have already described it. Eigenvalue of PC1 is just the sum of the squared distances of PC1. So pretty much when we are doing best fit, we are basically comparing the eigenvalues. When we calculate the sum of the squared distance, we'll be like, this line is 30, this one is 50, this one is 100. We're just comparing the eigenvalues, and we choose the one that is the maximum eigenvalue. It's called an eigenvalue of the principal component direction, right? And the square root of this eigenvalue is called the singular value. They are all interconnected, so don't worry about the terms. Singular value is just going to be the square root of the sum of the squared distances. The singular value, right? Or the square root of the eigenvalue of the principal component, square root of the eigenvalue. Cool, that's it, right? And like we said in the previous video, to get your PC2, you just find a line that is perpendicular to this. You find a line that is orthogonal to this, and you find that in this case PC2 is going to be equal to minus 0.242 gene1 plus 0.97 gene2. And it's just a matter of going to a graph. You'll be like, okay, which line is going to be orthogonal to that line? Okay, the line that is going to be orthogonal is going to be this one here. What happened there? I have no idea. Okay, sorry for that, just ignore it. Just ignore that part there. We're going to say this is going to be the line that is orthogonal to our first principal component, and this becomes our PC2. Easy like that. Yeah, so pretty much we've covered pretty much everything. We've pretty much covered everything that we needed to cover when it comes to principal components. In the next video, we're just going to describe something called a scree plot, but because I don't want this to be over 40 minutes. But in the next video, we're going to describe something called a scree plot. But we are pretty much done with how the mechanics of how the principal component analysis works. So stay tuned for that. It's going to be a very quick video. Yeah.